Did you know you're really good at physics? Seriously, you are. You want to know how I know? Go outside, bring your basketball, shoot a few hoops. Even if you're bad, and to be honest, I'm garbage. Like, my shot percentage is probably like 10% of the time it goes in, and that's when no one's defending me. Anyway, the point is even if you're not very good, you'll get a basket every now and then. That means you've tracked just how fast to throw that ball and in what direction. To work that out on paper would take at least 5 to 10 minutes, and your brain does it like that. It's crazy. It turns out that if you want to do this on paper, it's pretty hard, but totally doable. The first thing we need to do is to separate motion in the vertical direction, that is up and down, and the horizontal direction, that is left and right. And that's what we're going to focus on in this lesson. Remember, you could already do this out in your front yard, so let's learn to do it on paper. Let's begin by considering our lesson objectives. First, we'll learn to use the distance formula. Then we'll learn to split velocity into x and y components. Sounds kind of strange, but we can just think about the velocity in the x or the velocity in the y, and we'll explain just what that means. Then we'll practice component math with velocity and displacement. Everything we learn about displacement in this lesson will apply to velocity and vice versa. They can both be used with all of the math we'll do in the following slides. Okay, let's start with displacement. What is the displacement of the basketball for a good shot? Remember that displacement is the difference between the starting and ending position. So if we know something about the horizontal direction that it has to travel, say it's 3 feet, and something about the vertical direction it has to travel, say it's 4 feet. We could measure those, for example, with a tape measure. Then we can solve for this dashed line here, which represents displacement. All right, let's remove our picture and just think about this triangle. We'll call that 3 feet the horizontal direction x, and 4 feet, which is the vertical direction, y, just like we would on a graph. The dashed line then is d. What does it stand for? If you said distance, that would be incorrect. Remember that distance and displacement are not the same thing. And here we're solving for displacement, just the difference between the starting and ending location. All right, well, what equation relates all these sides? If you said the Pythagorean theorem, you're right, which normally we represent as a squared plus b squared equals c squared. Here, if we put it into the correct names that we have here on our triangle, we get d squared equals x squared plus y squared. Okay, well, what can we substitute in here? For x, we can put 3, and for y, we can put 4. So we'll get d squared equals 3 squared plus 4 squared. 3 squared is 9, and 4 squared is 16. So that becomes 9 plus 16, which is 25. Now, how do we solve an algebra problem where we have an exponent, that d squared? The exponent is that number up top. Well, we get rid of it by taking the square root. And what we do to one side, we have to do to the other. So we take the square root of both sides. The square root of d squared is just d, and the square root of 25 is 5. So we get d equals 5. So that's our displacement. Now we need to add units, which would be feet, because our x has the unit of feet and our y has the unit of feet. So our answer is going to have the units of feet. So what is the displacement of the basketball for a good shot here? 5 feet. 5 feet. All right, let's look at another situation involving displacement where we're going to use some different math also involving triangles. Here, hikers climb a steep mountain for 3.4 miles. To what height did they climb? Assume that the average slope was 30 degrees above the horizontal. How do we solve things like this? Well, this is going to use sine and cosine. Let me show you how. Whenever I have a triangle, the sine of the degree there, theta, is equal to the opposite length of the triangle divided by the hypotenuse. We'll define these terms in just a second. We can also use cosine of that angle and know that it gives us the adjacent length divided by the hypotenuse. All right, well, what do all those things mean? Well, the hypotenuse is just that longest distance. It's the longest side of a right triangle. A right triangle is just one with a right angle, that is a horizontal line and a vertical line meeting perfectly. What about an adjacent line? The adjacent one is the side of the triangle right next to the angle we're considering. So in this case, if we're looking at 30 degrees, the adjacent side is right there on the bottom because it's touching that 30-degree angle. You might notice the 30-degree angle is also made with the hypotenuse, but that's always going to be the hypotenuse, not the adjacent line. Lastly, we have the opposite side, and it's the side of the triangle across from the angle. So if we kind of draw a line from that 30 degrees to the farthest away side, that's always going to be the opposite side. All right, well, now let's go ahead and think about this in terms of the variables we've been using for a triangle. X for our horizontal direction, Y for the vertical, and D for that hypotenuse there. What this will let us do is rewrite our equations in terms of D, X, and Y. So we want to write sine theta equals opposite divided by hypotenuse, only we want to substitute in the correct variables for opposite and hypotenuse. Why don't you pause the video and give this a try for both sine and cosine? Were you able to get it? Here's the correct answers. The sine of theta is equal to y divided by d, because d is the hypotenuse and y is the opposite side. Cosine theta is equal to x divided by d, because x is the adjacent line and d is again the hypotenuse. All right, what we normally do here is we multiply both sides by d in these equations to get d sine theta equals y and d cosine theta equals x. We're going to use this over and over again in our problem, so it's a good idea just to memorize these equations. In this case, which one do we need? Well, we want to find the height, which is represented by y. So we'll use d sine theta equals y. We'll plug in 3.4 for the displacement and 30 degrees for our angle. That's going to give us y. Now, I want you to grab your calculator. If you don't have one, pause the video, go get it. Here's the trick. When you plug in these numbers, make sure your calculator is in degree mode. If you're not sure how to find if it's in degree mode or not, go to Google, type in the model number of your calculator, and say how to put in model number to degree mode, and it will explain how, okay? Now, when we plug this in and our calculators are in the correct mode, we should get 1.7 miles. So how high did those hikers climb? They hiked a 1.7 mile summit. Okay. The thing is, everything we've done here with distance, oh, did you hear me? I made a mistake. What was my mistake? I used distance. That's not right. Here, we've solved for displacement. Remember, those are not the same thing. And everything I've done here with displacement, I can also do with velocity. So here is an example where we can break our velocity into their x and y's components. Let me explain what I mean. That basketball is both going over to the basket and up to the basket. That means it has to have a certain velocity in the upward direction and a certain velocity in the horizontal direction. And just like we can solve for those components of our displacement with trig, we can do that same thing with our sine theta and cosine theta equations with our velocity components. Let's go ahead and solve for the vertical component of velocity. That is how quickly it's traveling upwards. There, we're going to want to plug in 2.1 for the initial velocity and 53 degrees for the angle. So we'll get 2.1 times sine 53 degrees. And again, if our calculator is in the right mode, we'll get 1.677 ... meters per second. Here, we're going to want to keep all of those digits if we're going to use this to solve a problem. Since the problem here is just determining the x and y components of velocity, we can go ahead and round. Because our 53 degrees and our initial velocity has 2 digits, we'll round to just 2 digits and get 1.7 meters per second. So that's the velocity just in the vertical direction. Let's do the same thing now for the horizontal direction. Here we'll use cosine theta. So we plug in the initial velocity again, and we plug in cosine of 53 degrees. When we do that, we'll get 1.3 meters per second, again rounding to just 2 digits. So now we actually know the vertical and horizontal velocity of that ball. Why is that important? Well, the forces acting on these two different velocities are very different. Because remember, gravity acts always downwards. So which one of those velocities is gravity going to interact with? The vertical one. Actually, the horizontal velocity isn't interacted with gravity at all. It just stays 1.3 meters per second the whole time. Let's summarize that. So for horizontal velocity, that is v sub x, it remains constant. It doesn't change. Meanwhile, vertical velocity changes due to the acceleration of gravity. So really important to keep in mind that our velocity in the x direction isn't impacted by gravity, but y is. Let's summarize what we've learned about our triangle math. X and y can be combined by the distance formula. So we get x squared plus y squared equals displacement. That same exact equation can actually be used with the components of velocity. So if you ever needed to recombine the components of velocity, you could do vx squared plus vy squared would give you that v initial squared. So if you ever need to recombine those velocity components, you can do that. All right, now what about the other triangle math we did? The one where we looked at the angles. Well, x and y can be found with an angle and a hypotenuse. And there we said that d sine theta is equal to y, and d cosine theta is equal to x. Well, just like we have those equations for displacement, as we've already seen, we have those equations for velocity. So you should write down all of these equations and realize that we use velocity and displacement in the same way in these problems. Let's now go ahead and apply these equations to solve a problem. All right, let's practice these ideas. First of all, you pause the video and give this a try, and then come back. All right, so we're told that a golf ball is hit with a velocity of 94 meters per second, and we're told the angle, 45 degrees above the horizontal. It's always nice to start these with just a little picture. So we have a golf ball going out at a velocity of 94 meters per second. And we know that the angle with respect to the horizontal is 45 degrees. We eventually want to solve for the vertical and horizontal components. So the horizontal component, it's right here, and remember that's going to be Vx, and the vertical component right there, and that's going to be Vy. We have two equations here for our Vy and Vx respectively, and we should recall that for our Vy, we always know that it's the initial velocity times the sine of our angle, which we call theta. And for our velocity in the x direction, we know that it's the initial velocity times cosine of theta. So let's go ahead and solve for Vy and Vx. So Vy is going to be equal to 94 times sine of that angle, which is 45. When we go ahead and plug that in our calculator, make sure you actually do this. Check on your calculator that you get the same answer as me. Okay, so what you should get is about 66.46. And now we'll round for 2 sig figs because our initial velocity has 2 sig figs. So we'll keep these two, and this guy tells me we're going to be rounding down. And so we'll just go ahead and get rid of that 0.46. Now, did you get that same thing? It's important that you did. If you didn't, that means you're probably not in degree mode. Notice that our angle is given in degrees and not what's called radians, another way to measure angles. If you're not sure how to change your calculator's mode, go ahead and Google that. If you Google your calculator model and change to degree mode, you should find it. All right. Now, what's the units here for our velocity in the y direction? It's meters per second. Okay. Let's actually change that to the same color. What do you think? Meters per second. Now let's solve for the velocity in the x direction. Again, it's going to be 94 times cosine now of 45. A funny thing about that 45 degree angle, because it's halfway between 0 and 90, it actually splits the velocity perfectly equally into the x and y, and so the x will give us the same thing to 2 sig figs, 66 meters per second. Okay, so that's splitting up our velocity into its components. Once again, go ahead and pause the video, give this a try, and come back. All right, were you able to get it? Let's go through it. It's nice to start with a picture. We know that the tee and the place that our golf ball reaches the maximum height are 120 meters apart. So that's in the horizontal direction. Meanwhile, the golf ball reaches the maximum height at 32 meters up. And we want to know the displacement, which is the shortest distance between its starting and ending point. So it's just the hypotenuse of that triangle. You might be thinking, hey, doesn't that golf ball make like an arc path to get to the highest point? And the answer is yes, it absolutely does. And if we wanted to calculate the distance, we would need the length of that white arc. But because we want the displacement, just the difference between the starting and ending position, we really want the dashed line, which is nice for us because that's a lot easier to calculate. Okay, so recall that the displacement, in this case represented by the hypotenuse squared, is equal to the x component squared plus the y component squared. And so to solve for d all by itself, we're just going to take the square root of both sides, and we're going to see what might look familiar to you as the distance formula. the displacement is equal to the square root of x squared plus y squared. And then we'll go ahead and plug in our x and our y. X is 120. Remember, that's in the horizontal direction. And our y, which is the vertical direction, is 32. When we square both of those and add them together, we'll get that we want to take the square root of 15,424. When we actually take the square root of that, we'll go ahead and get 124 meters. And that already has 3 sig figs. Technically here we'd want to round to 2 sig figs since our 120 there just has 2 sig figs. So if we did that, we would keep these 2 and the 4 would tell us to round the 2 down and we would get 120 meters. Okay, so that's the displacement we get once we round for sig figs. Let's summarize what we've learned. We learned to use the distance formula, which we learned really should probably be called the displacement formula, but the mathematicians called it the distance formula. We also learned to split velocity into x and y components. We saw that you can take a velocity and think about just how quickly it's moving in the x and just how quickly it's moving in the y. Lastly, we practiced component math with velocity and displacement, where we saw that all of that same triangle math can be applied to velocity or displacement.
Hey, hey.